Okay, this is lesson 5.1b. So simulation is just complete chance. It's based on a model, and it's usually done by computer, right? So usually there's lots and lots of trials, not just one, but maybe 100 or 500 sometimes. So the first thing you want to do is describe how to use a chance device to imitate one trial or repetition of the simulation. So tell what you're going to record at the end. What are we actually finding, that whatever we're counting usually. Perform many trials of the simulation. Usually that's just a repeatable process there. And then use the results of your simulation to answer the question of interest. So we're going to see how unusual our answer is compared to the simulation results we got. If it's outside of the simulation results, something's going on there. Okay, so in an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. I'm not sure if you're a fan of NASCAR, but if you are, you might recognize these 5 drivers. Each box of cereal has a collectible card that features one of those drivers. The company claims that each of the 5 cards is equally likely to appear in any box of cereal. I'm skeptical, but that could be true. So a NASCAR fan decides to keep buying boxes of cereal until she has all 5 drivers' cards. She is surprised when it takes 23 boxes to get a full set of cards. Maybe she's just unlucky. Maybe they didn't make an equal number. I don't know what the situation is. So does this outcome provide convincing evidence that the 5 cards are not equally likely? So to help answer the question, we're going to perform a simulation. So what would that simulation be? So you think about it. We could get out, a calculator, do the rand_int command, menu 542, I believe. So 1, 5, 1. So I picked driver number 4 right there. That's 3 trials. I've got 2 of them. 4, I've already got 3 different ones. 5, 6, 7, I just need 1. 8, wow, it only took me 8 times. That right away, like either maybe I'm really lucky or this person was really unlucky that took 23 times. So we just did a little simulation there. That's one trial. We would do many trials. Maybe figure out a way to do that faster or something on the computer, but that's the idea of what a simulation would do there. So how could you go about this? So let's look at the steps to do this. So it's similar to what we talked about last chapter. First thing you do, you assign numbers to all the people, right? So that sounds familiar. It sounds like something we did last chapter. So all 5 drivers get a number. You generate random integers, either using a computer or a calculator or something like that. You would describe that from 1 to 5. That simulates buying a box of cereal with a different card in it. Keep generating random integers until all 5 labels have been represented. And then finally, what are we finding here? In this case, we're recording the number of boxes it takes to get all 5 cards. So you have to verbalize that, right? That's what we're actually writing down. Whether that takes 8 tries that we did in our simulation, our trial, or it takes 23 times like it did when they did it. What does the .20 represent? Maybe you're getting better at this. The last chapter, I felt like this was a tough part. So 20 is one trial, right? That of many, that it took 20 boxes of cereal in the simulation in order to get all 5 drivers represented. One trial where it took 20 boxes to get all 5 drivers' cards. That's what they said. Part B, use the results of simulation to estimate the probability that it will take 23 more boxes to get a full set of cards. So where does 23 fall in the simulation? So if you look, it looks like 5. Wow, that happened like 4 or 5 times. That 5 people exactly, 5 boxes, got all 5 cards. That would be amazing. But it took, at most, it looks like 22. Twice, it took 22 tries. So 23 is really outside the range of chance here. So there's how many trials? There's 50 different trials here. So 0 out of 50 times you had the chance of doing that. So 0 out of 50 is a 0% chance that it would take 23 or more boxes for that to happen. For example, let me just change the problem slightly just to make sure you understand the probability part of this. Let's say that you had gotten a result of 18, We were trying to see how unusual that is. You see there's 3 dots at 18, there's 1 dot at 20, and 2 at 22. So 1, 2, 3, 4, 5, 6. There are 6 dots that are 18 or more extreme. So there's an 18 out of 50% chance, which is, or 18 out of 50 is like 36% chance. So there's a 36% chance that if you got a score of 18, that would happen just by chance. So, and that would not, we would not have enough evidence to say it's unlikely. I think we have enough evidence to say if 23 is really what we got, we say there's a 0% chance. Like, we can actually write the company and say, look, we've proved this with statistics. Something's funny is going on. You're not producing the same amount of each card. Okay, so here's just a problem. We're done with the lesson part, but let's just apply it to one or two problems here. So in a certain AP Stats class of 24 students, 2 of the students discover they share the same birthday. Surprised by these results, because it's a relatively small class, 24, to both have the same birthday, the students decide to perform a simulation to estimate the probability that a class of 24 students has at least 2 students. So we're going to assume, and this is important to assume stuff like this, like that all birthdays are randomly distributed. Maybe in real life, you know, maybe one month is more popular than another because of summer or winter or something. But we're going to ignore leap years, and we're just going to assume that every day is equally likely. That's an important part of just talking about it. How would you use a random number generator? So I think you would probably, you know, do something like rand int 1 through 24. Right, so if we had a calculator out here, we'd say rand int 1 through 24, comma 1 maybe. And if we have 24 students, that would be the first student. So you go 2, 3, 4, 5, 6, 7, 8, 9, 10. Or you could do it this way. You could actually do 24. And see if there's any, if you mouse up there and press enter, you can see if there's any repeats in there, right? If there's a repeat, like I see 2 16s. So there's at least one pair of people that have the same birthday. So this, let's look at this chart. So what does this mean? It's important to understand a simulation when you see it. The thing that surprised me the first time I saw this is there's a lot of zeros. That makes sense. About half the time, roughly, I'm just guesstimating there, about half the time there were no matching birthdays. It's actually surprising how many times there were matching birthdays, but there's never one. Why is there never one? So let's think, if 2 students matched, let's say they both have January 12th or something as their birthday, then there's not just one student that has a matching birthday, it's 2, right? There's no way to get one person. You only match with yourself. So I think it's impossible to get 1. 3 is possible, right? Because if there were 3 people with a January 12th birthday, you know, that's possible. So you can have 3, but usually they come in pairs, like 2, 4, 6. But occasionally you have a 3rd person or 4th person or 5th person who might have the same birthday, potentially. So, I forgot to mention. So the steps there, the first step, label each day of the year a number, right? Because we're considering 1 through 65. You know, January 1st is number 1, January 2nd is number 2, etc. So use the random number generator. We did that. Represent 24 students. Record the number of students in the class who share a birthday with a fellow student. So you would do that. Explain what the dot 5 represents. So 5 is one trial where there were 5 people in the class who shared a birthday with at least one other person. So they didn't all share the same birthday necessarily, but they shared a birthday with another person. Yeah. Use the results of the simulation to miss anything on that? The dot 5, one trial. Yeah, good. Use the results of simulation to estimate the probability that a class of 24 students has at least 2 students with the same birthday. Okay, so then you would count the dots. You see all the dots in 2, all the dots in 3, 4, 5, and 6. Add those up. I'm gonna let them do that for me. So they counted 26 out of 50. So 26 dots are 2 or more. So there's a 26 out of 50 or a 52% chance of getting results of a class of 24 students that will have at least 2 students with the same birthday, assuming birthdays are randomly distributed. Because this probability isn't small, 52% chance, that's very much within the bounds of that simulation. So in fact, it's all smack dab in the middle. It's pretty close to that. So we are not surprised at all by that result. About 50% of the students' number of trials we did came up with that result. So there's nothing unusual about that at all. What's surprising, I think, about that birthday problem is you would expect there to be a lot more zeros, but that's not usually the case. If you have 24 students in the room, you have pretty close to a 52% or around 50-50 chance of having two people with the same birthday, just roughly speaking. So it's kind of interesting. You would expect it maybe less of a chance of that happening. Okay, that's your lesson for today.